Hello, discrete math fans. I'd like to talk about tiling problems. Now suppose we have a 1 by n chessboard. That's kind of a weird chessboard. It's only got one square in one direction and n squares in the other direction. This is a 1 by 10 board. And what we're going to do is tile this with dominoes and monominos. Dominoes and monominos look like this. This guy here is a domino. It will fit two squares on our board. This is a monomino. It's just half a domino. Or maybe a domino is two monominos stuck together. Here is an example of a tiling of a 1 by 10 board. So what we've done is chosen dominoes and monominos to fill it up. Can't have any dominoes hanging off the end. What we'd like to do now is count how many ways there are to tile 1 by n boards for various values of n. Now when you have a 1 by 1 board, there's only one thing you can do, and that's just put a monomino on it. And there are two ways to tile a 1 by 2 board. You can either stick down two monominos or put down a domino. Okay, so one way to tile a 1 by 1 board, two ways to tile a 1 by 2 board. There are three ways to tile a 1 by 3 board. You can either put down three monominos or one domino and one monomino in two different ways. All right, so one way to tile a 1 by 1 board, two ways to tile a 1 by 2 board, three ways to tile a 1 by 3 board. So obviously, we know how many ways there are to tile a 1 by 4 board. Right, there are 5 ways. Wait, what? That's right, there's 5 ways to tile a 1 by 4 board. 4 monominos, or 2 monominos in 3 different ways, or 2 dominoes. So wait, 1, 2, 3, 5. How many ways are there to tile a 1 by 5 board? 8. There are 8 ways to tile a 1 by 5 board, and I've shown them all here. Had to make the boards a little bit smaller. All right, so the number of ways of tiling the 5 smallest boards are 1, 2, 3, 5, and 8. Fibonacci numbers. All right, so that leads us to guess this theorem. The theorem says that the number of ways of tiling a 1 by n board with monominos and dominoes is f sub n, where f sub n is the nth Fibonacci number defined by f1 equals 1, f2 equals 2, and for n bigger than or equal to 2, f sub n plus 1 equals fn plus fn minus 1. And we're going to prove this now. This proof is going to be by strong induction, but it's also going to be a combinatorial proof. So let's let t sub n be the number of ways of tiling a 1 by n board with monominos and dominoes. And for n in the natural numbers, let's let p of n be the predicate that t sub n is equal to f sub n. And we know that p of 1 and p of 2 are true because we already showed that t1 is equal to 1. We know f1 is equal to 1 by definition. We showed t2 is equal to 2, and we know by definition f2 is equal to 2. So t1 is equal to f1 and t2 is equal to f2. So these are going to be our base cases. Now let's let n be a natural number, n bigger than or equal to 2, and we'll make a strong inductive hypothesis to assume that p of 1 through p of n are all true. Now let's think about a 1 by n plus 1 board. And so that's kind of what we're visualizing here. It's a really long board. And first we'll ask, how many ways are there to tile this 1 by n plus 1 board? So here we're doing the combinatorial proof. Our first answer is, as we previously defined, there are t sub n plus 1 ways to tile this board. Now there's a second answer. Notice that no matter how we tile this thing, the end has to be either a monomino or a domino. Those are the only choices that we have. Here is a 1 by n plus 1 board that ends with a monomino. Now the number of ways to tile a 1 by n plus 1 board that ends in a monomino is t sub n. Because once you place a monomino at the end, then what's left over, this portion here, is a 1 by n board, and we know by our definition that that's t sub n. But t sub n is the same as f sub n, the nth Fibonacci number. What about a 1 by n plus 1 board that ends with a domino? Now, the number of ways to tile a 1 by n plus 1 board that ends in a domino is t sub n minus 1. Why is that? Once we've covered up two spaces with a domino, then what's left over is of size n minus 1, and the number of ways of tiling that remaining board is t sub n minus 1 by definition, and by our induction hypothesis, that's the same as f sub n minus 1. So, that means the total number of ways of tiling our 1 by n plus 1 board is the sum of these two, which is fn plus fn minus 1. And by our Fibonacci recursion, that's equal to f sub n plus 1. Therefore, we can say that the number of ways of tiling a 1 by n plus 1 board is equal to f sub n plus 1, and therefore p of n plus 1 is true. So, by the principle of strong mathematical induction, p of n is true for all n in the natural numbers. So, what have we proved? We proved that the number of ways of tiling a 1 by n board is equal to the nth Fibonacci number. Okay, that's all for now.